Bienvenue, welcome everybody. My name is Jasmine Rafati Fowler. I'm on the board of Alliance Française in Los Angeles. And Alliance Française here is very honored to have this event in collaboration with the French Consulate here in Los Angeles. And at Alliance Française, we promote the French language and French culture. We have classes in person, online, for adults, kids, and teens. We also have summer camps for teens and kids. And we start back here in September, so please join us, take classes. Follow us on Instagram to see updates on classes and on our workshops. And also visit our website. There's going to be Q&A after the presentation. It can be in French or English. Also, please don't forget to get your validation parking tickets when you're leaving. We put the validation first, then the parking ticket. Now it's my honor to present Nathalie Soara.
Thank you.
Sure.
Hello, good evening. Dear guests, let me first say how happy I am to introduce this Café des Sciences to those of you here at the Alliance Française de Los Angeles and to those of you who are attending remotely across the United States, France, or in other regions of the world. Today's Café des Sciences is part of a series of events organized by the Consulate General of Los Angeles with a focus on Europe, as France currently holds the presidency of the Council of the European Union. We are fortunate to have such talented speakers as Dr. Jean-Paul Guillet, who is professor at Université de Bordeaux in France and visiting professor at University of California, Los Angeles, as well as Dr. Mona Jarrahi, who is professor of electrical engineering at UCLA. Both perform their research in the field of Terahertz Waves and will illustrate the demand for collaboration between France, Europe, and the United States to develop new technologies. Their research and discovery are of great interest, particularly since terahertz have application in many fields, such as telecommunication, materials analysis, biomedical analysis, or for analyzing artworks such as paintings. I would like to thank them warmly for sharing their research with us this evening. Before giving the floor to our speakers, I would also like to thank our partners, the Alliance Française de Los Angeles, represented today by Jasmine Rafati for hosting this event, and Los Angeles Accueil, that is dedicated to welcoming, informing, and integrating members of the French-speaking community of Los Angeles. It's always a great pleasure to work with you on such events. Finally, I encourage you to follow the Consulate General of France in Los Angeles on our social networks so you can be informed of future events organized by our Science and Technology Service, composed of Alexis Bonafont, Clara Devoissou, and Karim Belarbi. I wish you an excellent Café des Sciences. And now I'll give you the floor. So which one want to begin?
Thank you very much. Thank you very much for the kind introduction and having us here today. Today I would like to give you some general background about terahertz waves, why they are of our interest, and some applications. And Jean-Paul will focus more on some specific applications related to art and conservation. So first, I guess you're all familiar with electromagnetic spectrum. We use it in different domains, starting from radio frequencies. Of course, our radios, mobile phones operate at this frequency. On the extreme, we have X-rays, which obviously has made our lives much easier. It's hard to imagine how we would have lived without X-rays. Ultraviolet light, visible light that we get freely from sunshine, infrared radiation that any heated object emits. And somewhere between these extremes, there is a part of the spectrum that there are not that many gadgets available that you use in your everyday life. I meant examples of different parts of spectrum, and you have seen use of these waves. But How many of you have you heard about terahertz waves or used it in your everyday life? So for long, this part of the spectrum was called terahertz gap, not because the waves are useless, because it was hard to get to this part of the spectrum. Why? In the radio frequency range, we have transistors, circuits that build your mobile phones and radios. They work very well, but as you increase the frequency to come to this regime, they have a cutoff. They cannot handle the speed because of good physical reasons. That's why all those electronic gadgets have very limited efficiency in this range. On the other side, in the visible range, we have X-rays, we have X-ray sources, we have lasers that work beautifully, but they rely on specific properties of materials that allow us to laser light, which unfortunately, again, don't work when it comes to this frequency. So there has been a technological limitation to access this part of the spectrum, and that's why we don't have that many gadgets. However, it turns out that the waves in this part of the spectrum have very unique properties that make it attractive for researchers like me and Jean-Paul. So the first reason is that it appears that most molecules and chemicals have very unique responses to the terahertz waves. It is really coming from the fact that the spacing between the atoms and the chemical bonds that atoms have somehow allow them to resonate with terahertz waves. Why is it important? It's because by shining terahertz on an unknown chemical and looking at its response, we can tell what kind of chemical we're dealing with. Not only that, a lot of media and materials are opaque to light. You cannot diffuse light through these books to see what is written. You have to open that book to see. However, terahertz waves can penetrate to a lot of optically opaque materials. Not everything, but many of them. So this allows us to access environments that are visually inaccessible to us. Also, water molecules highly absorb terahertz radiation. And later I explained that enables a lot of interesting biomedical applications because in our body, different tissue types have different water content. So the contrast in terahertz image we get because of this water absorption is a lot. And last but not the least is that we should not forget that these are safe radiation compared to X-ray, ultraviolet, or even visible light because they're very low energy. As frequency of the waves go up, their energy goes up. So in the terahertz regime, the energy is way lower than sunlight that we receive. So it's safe to use it in everyday applications. So can we go to the next slide? Okay. So here I would like to mention some of the applications that are my favorite list. First, as I mentioned, medical imaging. Since different tissues have different water content, they have a very unique contrast when you shine terahertz on. Here I give two examples. There are many more examples. I think Jean-Paul maybe mentioned some other examples. Here is the visible image of skin that has melanoma. As you can see, there is some abnormality in the coloration, but it is not as much as what we see in the terahertz range. It is a very large contrast. So that allows us to detect cancer at very early stages. Another application that is used currently in clinics is for assessing burn wound. So terahertz, because it has unique properties in absorbing, water absorbs terahertz highly. When you want to assess how much burn wound you have, what is the level, what is the degree, how much burn propagated, how close it got to your bone, which are very important because you have to quickly decide what medication to use, terahertz is a good sensor of that. So here, for example, is a visible image of a tissue that has burn on it. Of course, these are artificially made. And these are terahertz images. As you can see, there are very high contrast and details that you don't see in the visible range. In fact, we have collaborators in Washington Burn Center that they're using our terahertz sources to assess burn wound, and these are images from that group. Another example I should mention is that that is another attractive application is that in very early stages of tooth decay, when no physical damage happens to the tooth. So if you go to your dentist, they don't see anything on X-ray. A lesion starts forming in the tooth that has a different water content. So you can detect it with terahertz, and that's another potential medical application. Now, if we go to the next slide, security screening obviously is another application, both because we can detect chemicals from a remote distance and because we can see visually inaccessible environments. So I'm sure you have all passed through airport security. You separately pass your luggage through X-ray. Of course, you're not exposed to X-ray. You pass through metal detectors, but metal detectors can miss a lot of things. For example, here is a ceramic knife that metal detectors cannot detect, but terahertz images can see. Or different contents in a bag is you are able to see the details. Actually, right now, the highest frequency scanners, airport security scanners that are used, I believe, in Germany are around 0.3 terahertz. So they are not yet very high frequency. So if we advance the technology, then we can increase the resolution of the image. We can even detect images from farther distances. Also, in terms of chemical, as I said, molecules have very unique response to terahertz radiation. This is the response of different plastic explosive to terahertz radiation. So this is a logarithmic scale because here the aim was to fit in all these graphs in the same place, but in linear scale, these are very distinct peaks. So here at a distance, you can tell what kind of explosives you can have. Or illicit drugs. Again, here visually you see three powders that all look the same. They're white powders. But some of them are illicit drugs. Some of them are aspirin. So with terahertz waves in a non-invasive way, you can detect what kind of chemical you're dealing with. In fact, this area after 9/11 poured a lot of funding in our field because there was this big fear of anthrax being mailed to politicians. And of course, one can detect potential existence of them without even opening the envelope. Pharmaceutical industry is a domain that is using terahertz waves for two main applications. First is to detect the coating thicknesses that a capsule has. So the number of coatings a capsule has, their thickness, their material, are all planned well so that the drug is released at the right place in the body. So if these thicknesses change or if there are defects in them, then the drug is released instead of intestine is released in your stomach. So there will be a lot of problems. So with terahertz waves, one can very accurately measure these thicknesses and also see if there are potential defects in it. And that's why pharmaceutical industry is using it. Not only that, you can basically see if the right dose of chemical is used in a drug. So in pharmaceutical manufacturing facilities, they're dealing with very gigantic facilities, and there is a chance that dosages of chemicals are not managed right. But with terahertz, you can see the dose. Another problem in pharmaceutical industry is that a lot of times you put the right chemical composition in a capsule, but they end up crystallizing in different ways. For example, because of temperature change, humidity, and that's very important because it really affects the effectiveness of the drug in the body. And terahertz, because it really sees the interactions between molecules and the resonances of molecules are different, it can even tell if the right crystalline form of the drug is used. The other one. Astronomy and astrophysics applications is another application that I would say is probably the oldest application that really helped advance terahertz technology a lot. So we have a huge universe that we don't have access to it. And we need to learn a lot about other planets, other galaxies, how stars are formed, how galaxies evolve. And well, they're not accessible to us. It happens that every interaction that happens, even in far galaxies from us, involves some chemical processes that release gases, and those gases have a specific signature, a spectral signature that's close to Earth or out of Earth atmosphere. We can see those signatures. So here are terahertz images taken by Herschel Observatory, which was an observatory managed by European Union, that basically looked at different parts of, I think this is Orion Nebula. So the colors you see here are referring to different frequencies in the terahertz spectrum. So for example, by knowing how different frequency distributions are distributed, you can say what kind of water molecules involved, what kind of carbon ions are involved, and learn a lot about our universe. In fact, in 1980s, one of the Nobel Prizes went to terahertz technology that allowed scientists to learn a lot about Big Bang. So out of Earth atmosphere, there is not much loss for electromagnetic waves. So the information from Big Bang is still existing, and with very sensitive terahertz sensors, scientists were able to reveal a lot of details about Big Bang. The next application. Okay. Industrial inspection is another attractive application that is commercialized. Now you see some factories, some manufacturing facilities using it. I guess, again, Jean-Paul probably has some information about it. In semiconductor industry, these semiconductor wafers that are building blocks of the chips, electronic chips that you use in your electronic gadgets, can have impurities, can have variable parameters that with terahertz waves in a non-invasive way, you can detect those variations. In auto industry and in aerospace industry, you can in a remote way and in a non-invasive way detect the integrity of different paint layers, coating layers, thermal insulators, which are very important for spacecrafts with terahertz waves. For food quality and agriculture applications, again, you can see the integrity of the products and you can see the freshness of the product. For example, here you see the image of a leaf after 48 hours. Visually, you might not see much difference, but with terahertz imaging, because water content can be sensed very well with terahertz waves, you can know the freshness of the product. In fact, in our group, we are working with US Department of Agriculture, where they're very concerned about aflatoxins in agricultural food products. Aflatoxin, nobody knows really how they're introduced to our food products. They can exist in nuts, in different kinds of crops. Some believe they come from insect damage, but unfortunately, there is no way to know really if a product has aflatoxin unless you really crush that product and do mass spectroscopy, which means you're not able to use it. In fact, aflatoxins can cause serious health problems. Most importantly, they can cause liver cancer. So this is a major health concern, especially in California, that we have a lot of nut products. So with our collaborators, we have tried detecting aflatoxins using terahertz waves in a non-invasive way. And we were able to detect concentrations up to FDA levels. And now we're continuing our collaboration to increase the throughputs to maybe even use it as a regulatory standard in crop distribution and packaging centers. Biological sensing is another application, which is more on the research domain. So basically, I think you're all familiar with genome sequencing, especially during pandemic. We have all given PCR tests, so we know how important they are. So there are different kinds of genome sequencing technologies that are very advanced. Actually, it happens that terahertz can also be used for genome sequencing, although it's not probably the most cost-efficient technology. So I don't think it will have a good commercial application. But the idea can be used for other biological sensing applications. Basically, in any biological process, whenever a process happens, the biomolecules are either bonding to new molecules or breaking their former chemical bonds. All of these change their terahertz response, and through that, we would be able to, in a non-invasively, understand the dynamics of these processes. Other applications? Okay. So I will mention about very briefly the kind of research we do in my group. So I mentioned to you that the applications are very exciting. I mentioned, however, that terahertz frequency range is very hard to access. Electronics don't work, photonics doesn't work. So what we are doing in our group, together with many other research groups, is that we combine photonics and electronics together in order to introduce new physical processes to be able to generate and detect terahertz radiation more efficiently. So this is just a cartoon of some of our projects that shows that we use light sources from lasers that are very advanced technologies. And we basically design semiconductor nanostructures. I don't want to get into details of the physics that interacts with these light waves, and they convert light energy to terahertz energy. And they can operate reverse. They can receive light and terahertz waves and generate electrical signals that are really the measure of sensing of the terahertz waves. We are making spectral sensing devices that work both active or passive. Active meaning that there is a chemical there, I shine terahertz to look at its response and try to detect chemical. Or passive, like astrophysics applications, the chemical is too far from me. I look at what I'm receiving from space and try to make very, very sensitive sensors to detect those radiations. We are making a large area terahertz detector arrays for the first time to do imaging like normal cameras. In fact, my student Shurang is here. This is a work that he has done, and now he's collaborating with Jean-Paul to use it for applications. Also, we try to artificially make new types of materials, which we call metamaterials, that don't have the properties of natural materials, but it happens that when we put together a very tiny semiconductor and metallic structures, we can generate properties that natural materials don't offer. So through that, we do different manipulations for spectral and spatial properties of terahertz waves. The applications that we take in my group range from basic scientific studies that we do in the lab. We actually do astrophysics studies. One of our receiver systems is now prepared. We are preparing it to launch it on a telescope in Arizona to do astrophysics studies. I mentioned we work with US Department of Agriculture, different medical groups to use our technology for medical sensing. Also, we have a spin-off company from my group where we are using our current technology for industrial quality control. In fact, the applications are in auto industry, in semiconductor industry, in battery industry. In general, we can see the integrity of the products with a high throughput. I mentioned semiconductor industry. That's actually a new domain we are working. It happens that now that a lot of semiconductor device packaging is done in East Asia, there is a lot of fear of tampering with electronics, espionage, different kinds of things that can happen. And with terahertz, because we can see details of the electronic packages that cannot be seen directly, we can detect those kinds of threats, and we are collaborating with Intel on that project. So with that, I would conclude my talk. And the last slide, I want to mention that all the exciting work is really done by great students that we have in my group. Here, we have very diverse students from very diverse backgrounds, almost from all continents. in the world, and they're energetic. That really gives us a lot of excitement to work with these bright minds, innovative individuals, and all the work credit goes to them. I would like to thank take you any questions that you have, and thank you for listening.
Okay, thank you. So good evening, everybody. So first, thank you, Clara and Karim, for the organization and the consulate and the Alliance Française. So since Mona presented very well the Terahertz Wave, I will focus more on the application. So I will just present some applications, and I will focus on art because you are here for that. So before to present the art application, maybe I will just present a few applications and real measurement that I did in my lab in France. And of course, it's European projects, since you know it's the presidency of Europe during 6 months. It's France who is presidency. In fact, a lot of projects in Europe are collaborative projects with the European countries. So first, that one, for example, it's still ongoing project. We are working on breast cancer imaging. Mona presented some application on biomedical, and this is for breast cancer. So in fact, after surgery, we want to check if there is a matching or not. That takes a few days, and after that, in some cases, the women have to do a second surgery. In 10% case, it's a lot. In fact, the goal is to do fast imaging. I mean, during the surgery, just after the surgery, we still have 20 minutes when we still can remove a little bit more. And we want to do that imaging without any marker and any process. And we shown that using Terahertz, we are able to do fast imaging directly on fresh tissue and to detect that cancer. Another example of project, it's a European project on aeronautics and aerospace. And we work on composite materials. So this is an example of radome. It's the nose of the plane. Mm-hmm. So we were able to detect some defect inside that composite materials. Another example of projects about additive manufacturing for medical implants. So we can do now some medical implant in plastic or ceramics. And in that project, we use Terahertz to check accuracy and the object to see if there is defect or not before the implant. And then the last example, so Mona also told a little bit about that. So it is a project we had with the French Post and the German Post to check the parcels and the envelope. So we were able to detect some explosive, and also we were able to detect some mixture of explosive and to detect the signature of that without opening it, of course. Okay, so just a few examples of images from my lab. So you can see that we can use Terahertz to see through wood, through a bag. You can see through a pottery. We can do imaging also, for example, in that box, we can see that number. So it's an example of images. So we do a lot of images for research project, also for project with industry. So this is an example of image. You see, this is at high frequency, almost 3 terahertz. And then another example here with plastic. So you see, we have a lot of examples of application. So now I will focus more on art, but before that, I want just to show you an example of Terahertz system. You know? Because most of these systems are based on a laser, so it's quite complex to show because it's big, you cannot bring it. But that system is low frequency Terahertz. It's 150 GHz, so it's 100 times higher than 5G. And you can see this is the system. Here it emits the Terahertz wave. And then we use a lens, you know, like a lens. You see the curve here. And that lens, in fact, focuses the wave here. It's transparent, in fact, for Terahertz. Okay. So that is transparent, and it focuses the wave here. And we can use that to measure one point. And then, of course, if we move that on a painting, for example, we can measure for each point, and we can create an image. Okay. So okay. Oops, sorry. No, that's wrong. So if you want. Okay, so this is the system. Then you can see. Okay, you can see the object. So we move the radar and can measure for each point and create an image. Like this. So now I will focus on art. So first, an example of measurement I did maybe 4 years ago on a painting. So it's 17 painting. It's 80 by 60 centimeter. And the goal here was to help a restorer to detect the defect and to help her to do the restoration. So you can see first an image, an example of image. This is an image at 300 GHz. And you can see that we see some features here that are not visible on the image. We can see some defect here, some cracks on the visible range. But in some case, we cannot see that in the visible range. So we did a lot of images. In fact, we cannot say that we can use a Terahertz system just to do image and we have one result. In fact, depending on the frequency, depending on the system, depending if it is in transmission or in reflection, we have different images. So this is very interesting because we have a lot of data. We can create a lot of images, and we have to do a lot of data processing to reconstruct all these images. So why we use Terahertz? So when we want to analyze paintings, in fact, we can use the UV for the varnish layer. So it's useful to detect some defect. Then the visible range for the picture layer, infrared to go deeper to the cord, and then we can use X-rays to see through the painting. Okay, so this is the classical method. But now we can use Terahertz, which is a technique which provides a very interesting result because we have the capability like X-rays to see through the object, but we have also the possibility to have some reflections of each layer. And that's not something we can get with X-rays because with X-rays we have an image that provides a view of all the slice, and we cannot make a slice and see detail for each layer. So I will show more in detail some examples. So on the 300 GHz transmission image, we see some bubbles here. So with the help of restorer, so I'm not a specialist of interpretation of that image, so I work with some restorer and conservators to understand that. So in fact, that painting was relined. So in fact, there are two canvases, and with a glue, in the past we did a restoration, and in fact we see the glue between the two layers and the two canvases. Then another image at 100 GHz. It's interesting because it provides another explanation. So the art restorer saw that, and she can understand a lot of things that I didn't see. In fact, that painting was in the past rectangular shape, because at some period it was more famous or more interesting, more beautiful to have a rectangular shape, but some people wanted then to modify and to have an oval shape. So that painting was a long time ago restored, and they changed the shape of the painting. And we can see that because in fact, here at that part, the painting is different. In fact, when we analyze that, we see that this is the original painting with the rectangular shape, and then the oval shape is an added part of the painting. Then, if we look at 300 GHz, it's another image that we can generate. In that case, we see what I presented before. So we see some detail here. That was not possible to see in the visible image. We see also some defects here, but it was possible to see. But very interesting, that one. So to understand more what are that defects, we use another system pulse laser. It's something like we use with Mona here. It's interesting because we have a better resolution compared to the radar system. So with that system, we were able to get the image and to create some slides. It means that we are able to cut the virtually. We are able to cut the painting and see the different layers. So we can do some cut here, and you can see that. And of course, we see the different layers. There is the varnish, the pictorial layer, the canvas. But for that, they cut corresponding to the defect. We see that we have a gap here. So we have a few micrometer gap of air, in fact. So we analyzed that, in fact, it was a defect. It's quite common. It's an air gap between the picture layer and the canvas. So it's impossible to see when you see the painting, but it is a preliminary identification of aging. And after that, it can crack, and that picture layer can be crushed. So it's important to detect that. And we were able to restore the painting and to do preventive preservation. So in fact, she prepared some old-fashioned glue based on fish glue and rabbit skin glue, all methods, I don't know. And she prepared some glue respecting the old-fashioned methods, and she inserted that glue in that little air gap, and then it was restored, and we can see we did another measurement after that, and we no longer see that defect after the restoration. So in fact, we can detect the restoration, the defect, and then we can check if it was restored or not. So after that, we did a lot of measurement. I will not present all the images, but this is another example of painting. So this is before restoration, during restoration, and after restoration. And in that case, also we were able to detect some defect like in the previous painting. We also, in my lab, we developed some systems. This is another system which is a little bit like the radar I show you, but it's an open source, open science system. So you can develop your own system, in fact, using all the information, and it's quite cost effective. So it's interesting that we also work on some collaborative open science systems. Now I will present another analysis. So to show you all the capacity of Terahertz Waves. This is a Jerome Bosch school painting with very precise details. And this is a painting on copper, on metal. It's quite challenging for restorer when you have a painting on metal. And on that project, we wanted to detect the aging of the varnish. Today, we do that with ultraviolet, but in fact, we just have an image and we don't know how is it aging or not. So we don't know exactly if we should restore or not that painting. So we use some techniques using the Earth system plus a lot of data processing to be able to reconstruct the different layers. It was done by my PhD student, Quentin Cassard, who just started now a spin-off company, and she started in France, in Bordeaux, a company. So he developed some numerical methods to reconstruct the different layers, varnish, the pictorial layer, and the adhesive layer. So we can see the 4 layers. Here you cannot see some peaks. You see, because it's very thin and all the peaks are mixed. But by doing some data processing, we can reconstruct that and we can measure the distance of each layer. And that is useful to detect some areas where the varnish was old, and then we did a restoration. Okay, so I present now some other work. It's not my work, but to show you some example. We can see through a painting, we can see different layers. We can also use that not only for restoration, but also for conservation, to understand the painting, to see some details and to see some drawing of the painter below the painting. Another example, quite famous, is the ability to detect pentimento. So we can see a painting which is behind the painting. So you see here the painting, but in fact, in the past, there were another painting behind. It's quite common because the price of the canvas was very high in the past. So most of the painters reused old canvas to paint on this. So this is the visible image. This is X-rays image. It's not terahertz, but we can see that with terahertz we can also detect the same. And of course, it's better to do that because we have also information on different layers, and it's not it's safe. I mean, of course, we can do that with X-rays, but with that technology, it's safe, and we can also have some information of the thickness of different layers. So I talk about paintings, but I can also talk more about heritage. So it's an example of Egyptian clay vessel. It's two different papers. We can do imaging through big pottery. So in fact, depending on the object, we will use different terahertz systems. I will not detail more, but there are different terahertz technologies. When we want to do imaging on that kind of object, we use low frequency but high power systems. And we are able to see through sealed objects. And for example, on that paper, it's in Bordeaux, we were able to detect what is inside the vessel. So we were able to detect some olive oil, something like that. So yeah, there's a lot of examples for art and heritage and analysis. Before to go to the end, I want just to talk a little about spectroscopy. So also Mona talked about that before. It's the same method like to detect explosive or drugs. So in fact, we can use that to detect pigment. So each pigment has a unique fingerprint, a unique signature. And in that paper, we were able to predict the signature based on the molecular structure of that pigment. Then with some quantum algorithm, we were able to detect and predict that spectrum. And then we did measurement and we get exactly the same signature. That is very interesting because we can check if the pigment that we buy are really old, ancient or not. Because sometimes they mix with some modern pigments. So it's interesting for that, maybe for the supply chain or to check the sample. It's not possible to do, in my opinion, on directly on the painting, to be honest, because a lot of people want to do that on the painting. No, it's not to do on the painting, it's more on pure pigments. You can check that pigment. So we can do imaging of paintings, of vessels. There are some applications on mortars, on wall paintings. There are a lot of applications. Maybe I can just explain you how we do that. In fact, we have some limitation because the time of acquisition is sometimes long. So most of the time when we want to do large image, like a wall, in that case, we will use the system I showed before. It's a radar system. So it's very fast and we can do 1 meter by 1 meter image in 30 minutes, for example. Then if we have some interesting zone, we can focus on that. And in that case, we will use another system, which is based on a laser, which provide a better understanding and more details. But it's slower, so we use that for 20 or 40 centimeters only. So just to give you some information on the state of the art and where we are. In fact, that research topic started maybe in 2010. some people like Kari Fukunaga in Japan and some people in Europe started to work on that using the laser-based system. But then the radar system is quite recent because that technology was developed only maybe 5 years ago. So that one is very new and there are not a lot of measurement yet in that system. And then to conclude, I think it's really a wonderful tool. In fact, it's very fun to work in that field because we can do image on a lot of things. We collaborate with art restorer, with industry. We can work with a lot of people from different fields. So it's very funny to work in that field. We developed some systems. So this is a system that is now in the lab in Los Angeles. You can see the radar. I show you with the stages. So it's something transportable, and we can do an image with that system. And then the challenge for us is to better understand what we can expect and what we can get from many objects. Because I did measurement from some paintings, some objects, but in fact, there are a lot of study cases that we could do. And today in the community of art restorer, that technology is not well known. And it's now the challenge for us to use that system on different study cases and to learn more. And for me, it's the challenge for next years. Thank you.
Thank you.